Hello everyone. So, in today's lecture we will start convective heat transfer in internal flows. So, we will consider internal flows through channels such as ducts, pipes and parallel plates. You can find the application in heat exchangers. While considering these internal flows, first we will assume the laminar flows. In general, for these internal flows through a pipe or circular tube, the Reynolds number based on average velocity and the diameter, if it is less than 2300, then we consider it as laminar flows. So, Reynolds number you know that it is a ratio of inertia force and the viscous force. So, this Reynolds number we consider as rho, average velocity um or mean velocity, and diameter divided by mu. So, rho is the fluid density and mu is the dynamic viscosity of the fluid. So, if Reynolds number less than 2300, then we consider it as laminar flows through pipe. So, in this study for internal flows, we will consider two different types of boundary conditions. One is uniform wall temperature, where we will assume the temperature to be constant on the walls, and secondly we will consider uniform wall heat flux, where we will consider heat flux to be constant on the walls. If heat flux is constant on the walls, then wall temperature will vary in axial direction. Similarly, if we consider uniform wall temperature boundary condition, then we will see that your heat flux will vary along the axial direction. In addition, we will study also the entry region and or developing region and fully developed region. So, you know that in entry region the boundary layer thickness will grow along x and it will merge at the center region. When the entrance region extends to the from the inlet to the section where this boundary layer thickness merges at the center line, and the fully developed region starts from there. So, what is the objective to study these convective heat transfer in internal flows? Obviously, the first thing is to find the temperature distribution inside the domain. So, once you know the temperature distribution inside the domain, then based on the thermal boundary condition on the wall, we will have these objectives. So, you can see that if you have uniform wall temperature, then our objective is to determine the axial variation of mean fluid temperature Tmx, which is also known as bulk mean temperature. Then heat transfer coefficient Hx, okay, your heat transfer coefficient will vary along the axial direction, and hence we will calculate the Nusselt number, and as it is uniform wall temperature, we want to find the wall heat flux. Okay. So, this is the wall heat flux which is function of x. Similarly, when we will consider the uniform wall heat flux, then we want to determine the axial variation of mean fluid temperature, axial variation of heat transfer coefficient, and hence we will calculate the Nusselt number, and also we want to calculate the axial variation of wall temperature. So, this is your Tw. So, wall temperature Tw, as I told that for uniform wall heat flux condition, your wall temperature will vary along the axial direction. So, now let us discuss more about the entrance region and fully developed region. So, as we discussed, in general we will consider at inlet you have uniform velocity u I and uniform temperature T I, where I denotes the inlet. Now, in the entrance region, as we discuss that your velocity boundary layer will grow and it will merge in the central region. So, up to this point, okay, from the entrance it is known as entrance region. First, let us consider the flow field only. So, you can see that you have a uniform velocity inlet at x equal to 0. In general, x will consider the axial direction, okay. So, in the central region, so this is your x, okay. So, this is your central line, so that is the x direction, and from central region now we will consider r, which is your radial direction. Okay. And we will consider u as axial velocity and v as radial velocity in 2 dimension case or axisymmetric case. So, now you can see that when velocity will enter in the duct, so your velocity boundary layer will start growing, okay. So, then it will merge at the central line. So, up to this point it is known as entrance region or hydrodynamic entrance region, as we are considering only the flow field. So, obviously you can see this is your velocity boundary layer thickness delta, and this delta is gradually increases and it merges at the central line, and this region is known as entrance region. So, you can see how the velocity profile will look like. So, obviously at the inside the boundary layer, so velocity will gradually increase from the wall and it will go to the core region. So, this is known as core region, and this is your viscous region, okay. And obviously this is inviscid flow region, which is your core region, inviscid flow region, and this is your boundary layer region, which is your viscous region. And at core region you can see you will have uniform velocity, and if you consider two different sections, so let us say this is your x1, and if you consider another section x2, then you can see that your core velocity will increase. Okay. So, if this is your core velocity, so this is if your core velocity is constant, if it is c at section 1, and if it is core velocity u c at section 2, then u c 2 will be greater than u c 1 in the developing region or entrance region. So, why it is so? So, you can see that your velocity boundary layer is gradually increasing. So, to have the same mass flow rate at section 1 and section 2, you should have more velocity at the core region at section 2. So, for that reason your core velocity at section 2 is higher than the core velocity at section 1. So, in this case this developing region, this length we will consider as LH. So, first is your entrance region, Okay. So, this is your developing flow, because you can see your boundary layer gradually increases and it is in between 0 x to L h. So, whatever here it is mentioned x fully developed h. So, that length we are telling that it is your entrance length, which is your L h. Okay. So, obviously, now the region, this entrance region is characterized by the following features. Okay. So, first thing is that so you can see that in the developing region your v velocity, which is your radial direction velocity, is not 0. Okay. So, obviously, for that reason your streamline will not be parallel in the developing region. So, the radial velocity component does not vanish. Okay. So, that means your V r not equal to 0 and hence the streamlines are not parallel. The second observation, already we discussed that core velocity, okay, you see increases with axial direction, and you can see that obviously pressure decreases with axial direction, pressure decreases with axial direction, okay. So, your dP by dx will be less than 0 and most importantly your velocity boundary layer thickness your delta is within the tube radius, Okay. So, delta will be less than r naught in the developing region. Okay. So, now once you can see that this boundary layer reaches to the central line and merges, then there will be no further growth of this hydrodynamic boundary layer. So, if there is no growth, then obviously your boundary layer thickness will be r naught in the fully developed region, and you can see that as there will be no development of this hydrodynamic boundary layer, your axial velocity u will not vary with x. So, that means axial velocity distribution will remain constant in the fully developed region, and hence del u by del x will be 0, and this is the condition for fully developed flow. So, now we are discussing about the fully developed flow region. Okay. So, it is characterized by the following features. Okay. So, first thing is that V r will be 0. So, radial velocity will be 0, hence the streamlines are parallel. Then for two dimensional incompressible flow, the axial velocity u is invariant with axial distance x. Okay. Hence, you can write del u by del x is equal to 0. So, you can see in this region, in fully developed region, so velocity becomes parabolic, and as your boundary layer thickness merges here, so your delta in fully developed region will be r naught. Okay. So, in fully developed region your delta always will be r naught, and at different section if you see in the axial direction, this velocity profile will not change. Hence, your del u by del x will be 0 in fully developed region. So, now let us consider the temperature field. So, similarly, when your fluid enters at the inlet, you have a uniform temperature T I. Now, when it will come into contact with the wall, which may have uniform wall temperature or uniform wall heat flux boundary condition, your thermal boundary layer thickness will grow and merge at central region, and up to that region it is known as entrance region, and it is known as the distance from the x equal to 0, it is known as thermal entrance length. And after that you can see that thermal boundary layer thickness will not grow further. So, delta T, which is your thermal boundary layer thickness, will be equal to R naught in the fully developed region. However, in this case your temperature distribution or temperature field will keep on changing with the axial direction in the fully developed region. Unlike in your hydrodynamic case where u does not vary in the axial direction, in this case as always there will be heat transfer from the wall to the fluid, your temperature profile will keep on changing. So, you cannot write in this case for two dimensional incompressible flow del T by del x equal to 0, it is not true. So, in this case entrance region so what is happening, you have uniform wall temperature T I at inlet. So, gradually your thermal boundary layer thickness delta T, generally we consider thermal boundary layer thickness delta T will start growing, and it will merge at the central region, and this distance is known as thermal entrance length, and this is your thermal entrance region. After that this region is known as fully developed region, and in fully developed region now your temperature will keep on changing in the axial direction. So, in the entrance region, so delta T is your thermal boundary layer thickness, okay, and when you have L T, if it is your thermal entrance length, then in the entrance region delta T will be less than L T. Okay. So, this is one condition, and also you have core temperature. Now, you can see this is your core region, it is your core region. So, the heat transfer is taking place from the surface to the fluid if Tw is greater than Ti, then obviously from the wall to the fluid there will be heat transfer, and inside this thermal boundary layer thickness there will be variation of temperature, but at the core region there will be the fluid will remain at temperature Ti. So, this is actually at temperature Ti. So, there is no effect of the wall temperature in the core region in the thermal entrance region, and if you consider two different sections, then you will see that your Ti will remain same at two different cross section, because your Ti will remain same in the core region. So, core temperature Tc is uniform and is equal to inlet temperature. Okay. So, your Tc will be Ti in the core region, and temperature or thermal entrance length or thermal boundary layer thickness will be less than Lt. Okay. And if you consider a fully developed region, okay. So, obviously, now in this case your delta T always will be R naught, okay, because there will be no further growth of this boundary layer thickness. So, if your R naught is the tube radius, then delta T will be always R naught, and in this case your fluid temperature varies radially and axially, okay, and in this case del T by del x not equal to 0. Okay, you can see it will keep on changing, and here we will define later one dimensionless temperature, phi is invariant with axial distance x. And in this case you can write del phi, in this case you can write del phi by del x is 0, and phi will define as T wall minus T, which is function of r and x in 2 dimension or axisymmetric case, and T w minus T m. So, it is the ratio of T w minus T and T w minus T m, where T m is the mean temperature. Or sometime it is known as bulk mean temperature or bulk temperature, So, in this case you need to calculate at that cross section what is the bulk mean temperature. We will learn how to calculate this bulk mean temperature later. So, this bulk mean temperature we can see that the difference T w minus T varies similar way as T w minus T m, so that your del phi by del x will be 0, and this is the condition is valid for both the boundary conditions, uniform wall temperature and uniform wall heat flux. And in this case you can see that if you have uniform wall temperature T w, so this is your T w, okay, we generally writing T w. So, this T w if it is greater than your T, then T I, then gradually your heat transfer will take place from the wall to the core fluid and from the surface to the fluid, and you can see that your temperature distribution will look like this, because this is the temperature T w, okay, and there is a temperature, and in the core region as T I is less than T w. So, it will have less temperature than the T w, and if you have uniform wall heat flux which is Q double prime W, then your temperature distribution may look like this. Okay. So, this is the temperature distribution in fully developed region, and please remember that in this particular case del T by del X will not be equal to 0. Here del phi by del X is 0, where phi is the non-dimensional temperature or dimensionless temperature as defined T w minus T divided by T w minus T m. So, as we are telling that T w minus T varies in similar way as T w minus T m, hence your phi is invariant with axial direction, and you can write del phi by del X equal to 0 in this particular case. So, now let us see how to find this hydrodynamic entrance length and thermal entrance length. Already we discussed that hydrodynamic entrance length we have denoted as L h, and thermal entrance length we have denoted as L t. So, first we will use the scale analysis and we will see what is the order of this hydrodynamic and thermal entrance length. So, we know from the external flows that, so first let us consider hydrodynamic entrance length, okay. So, L h, and we know from the external flows that delta by x is order of 1 by root R e x, okay, where R e we have defined R e x as your, in this particular case it will be u. So, this is your u, your average velocity x by nu. Okay. So, now at the point where these velocity boundary layer merges, then x at x equal to L h you have your delta is equal to R naught, right, delta is equal to R naught, or so you can write that the order of delta is at x equal to L h, order of delta we can write diameter of the tube. Okay. So, now we are doing the scale analysis. So, order of magnitude we are seeing. So, the thermal, so the hydrodynamic boundary layer thickness you can write delta as order of d. So, in that case now you can write d by L h, will be order of 1 by root R e L h. Okay. So, now R e L h what we can write, it is just u average, okay, u average, or u average you can write u average like this, or u mean sometime we can write. So, u average. So, you can write u average into your entrance length L h divided by nu. So, now we will convert it the Reynolds number based on the diameter. So, u average d divided by nu into L h by d. So, you can see that you can write R e d. So, this quantity is R e d, Reynolds number based on diameter into L h by d. So, now if you substitute it here, So, what you will get d by LH will be order of, so 1 by root REH. So, 1 by root RED and you can write root LH by D. So, now you can write this LH by D divided by RED, okay, to the power half will be order of 1. Okay. So, where LH is the hydrodynamic entrance length, D is the tube diameter and Reynolds number now based on diameter we have defined. Okay. So, LH by D divided by RED to the power half will be order of 1. Similarly, now consider thermal entrance length. Thermal entrance length, which you have denoted as LT. So, in this particular case you can see that whether Prandtl number is greater than 1 or less than 1, both cases the thermal boundary layer will merge at the core. Okay. So, in this particular case we will consider that velocity u is order of u infinity, okay, or u average. So, in this particular case the velocity will take the scale of u average, okay, irrespective of the low Prandtl number fluids or high Prandtl number fluids, because both will merge ultimately at the central region. So, in this case now u will consider as u average. Okay. So, for this case, so now delta T by x, you know that if you consider u is order of u average, then it will be 1 by root Rex into Prandtl number, right. So, that we have already shown for the external flows, okay, because it is a developing region. So, in the developing region you can see that it is kind of external flows and delta T, which is your thermal boundary layer thickness, is increasing with x, okay, and as we are considering the velocity scale as the average velocity irrespective of high Prandtl number fluids or low Prandtl number fluids. So, delta by x we can write as 1 by root Rex Prandtl number. Now, we can consider that x equal to LT, your delta T will be order of D, because that will be your the thermal boundary layer thickness will be order of diameter. So, you can write delta T diameter divided by LT will be order of 1 by root ReLT into Prandtl number. Okay. So, now you convert this ReLT as u average, okay, LT by nu. So, you can convert in terms of diameter. So, it will be d by nu into LT by d. So, this you can write now in terms of Reynolds number based on diameter into LT by d. So, if you put it in this equation, then you will get d by LT is order of 1 by root Red into Prandtl number into LT by d to the power half. Okay. So, this if you see, then you can write LT by d divided by Red into Prandtl number to the power half, okay, will be order of 1. Okay. So, for hydrodynamic case you have seen H by d divided by Reynolds number based on diameter to the power half is order of 1, and in this case as we are considering the thermal flows. So, it will be LT by d divided by Reynolds number based on diameter into Prandtl number, okay, to the power half will be order of 1. Okay. And now you can see the ratio of this hydrodynamic entrance length and the thermal entrance length will be, so LT by LH. So, if you divide, you can see LT by LH will be order of Prandtl number. okay. It will be order of Prandtl number. So, using scale analysis we have found that L h by d divided by R e d h to the power half is order of 1. So, now after solving numerically or analytically you can find this entrance length. So, now we will define the entrance length coefficient, you can see here entrance length coefficient. So, this is C h is known as hydrodynamic entrance length coefficient and it is given as L h by d h considering the hydrodynamic entrance length equal to C h, which is your hydrodynamic entrance length coefficient, into the Reynolds number based on hydraulic diameter, and you know that hydraulic diameter we define as 4 A f by P, where A f is your channel flow area and P is the channel perimeter, and for circular tube you know that diameter of this pipe will be your hydraulic diameter. Now, for thermal entrance length L T, we have seen that it is function of Prandtl number and Reynolds number. So, L T by d h is equal to C T into Prandtl number into Reynolds number based on hydraulic diameter, and this C T is known as thermal entrance length coefficient. So, you can see that this we can rewrite in this form L h by d h divided by R e d h to the power half is equal to C h to the power half, and this also we can write L T by d h divided by Reynolds number based on hydraulic diameter into Prandtl number to the power half is equal to C T to the power half, and this using scale analysis we have shown that both are order of 1. So, after doing analytical or numerical solution, these entrance length coefficients are found for different geometries. So, you see this table. So, if it is circular tube, then your hydrodynamic entrance length coefficient C h is 0.056 and C T, which is your thermal entrance length coefficient, it depends on the boundary conditions. So, for uniform wall heat flux C T is 0.043 and for uniform surface temperature it is 0.033. Now, if you consider a rectangular duct where sides are A, B as shown in this figure. So, if A is equal to B, then it is a square cross section channel. For that C h is 0.09 and C T for uniform wall heat flux it is 0.066 and C T for uniform surface temperature it is 0.041, and similarly for A is equal to 2B, A is equal to 4B and A by B is infinity, that means it is almost infinite parallel plates. So, for that also C h and C T values are shown. So, these are obtained from the analytical and or numerical solutions. So, now let us see that what we derived using scale analysis. So, how it matches with this analytical or numerical results. So, we have already shown that this is order of 1 using scale analysis, we have already seen, right. So, if you consider a rectangular channel of aspect ratio 2, then your C h is 0.085 and this to the power half is 0.29. So, you can see that scaling estimates the constant 0.29 to be unity. Similarly, if you consider for a rectangular channel of aspect ratio 2 at a uniform wall temperature, then for this you can see it is 0.049 and C T to the power half it will give 0.22. So, we have seen that using scale analysis it is order of 1, right. L T by d h divided by Reynolds number into Prandtl number to the power half is order of 1. So, obviously you can see that scaling estimates the constant 0.22 to be unity. So, in today's lecture we have first discussed about the objectives to study the convection in internal flows, then we have discussed about the hydrodynamic entrance length and fully developed region. We have seen that in fully developed region the velocity does not vary in the axial direction. So, del u by del x equal to 0, and when we considered the thermal or temperature field, then we have seen that in the core region your temperature will remain same as the inlet temperature in the thermal entrance region, but in a fully developed region your temperature will change gradually in the axial direction. So, del T by del x is not equal to 0 in this particular case. So, we defined one dimensionless temperature phi as T w minus T divided by T w minus T m. We discussed that T w minus T varies in similar way as T w minus T m, where T m is the mean temperature. Hence, this non-dimensional temperature phi does not vary in the axial direction. So, that means your del phi by del x equal to 0. Then we used the scale analysis, and we have seen the hydrodynamic entrance length L h by d divided by R e to the power half will be order of 1, where Reynolds number is defined based on the diameter. And when we considered the thermal entrance length, in that particular case your L T by d divided by R e based on diameter into Prandtl number to the power half will be order of 1. And we have also seen the ratio of L T and L h will be order of Prandtl number. So, in next class we will see that how we can find these thermal and hydrodynamic entrance length using analytical and numerical approach. Thank you.